In this video, I'm going to step through the mathematical procedure of performing regression. I'm going to start with linear regression and then talk about nonlinear regression. So let's first orient ourselves. So with linear regression, at least in the simplest case, we're interested in how x and y are linearly related. So in other words, the best fit slope and intercept. I believe I call that A1 and I called this A0. So we're trying to minimize the function SR, which is the sum I equals 1 to n of e sub I squared, which is equal to the sum I equals 1 to n of y sub I minus y sub I predicted squared. And remember that we are predicting that y sub I is equal to a0 plus a1 x sub I. So what we're trying to do is minimize S sub r, which is equal to the sum I equals 1 to n of y sub I minus a0 plus a1 x sub I squared. So remember, students can get disoriented with the process like this because I think people are naturally wired to think of x and y as variables, but that is not the case in this problem. X and y are your data, right? They're what you measured. So in other words, the positions of these points, and unless you are a rather dishonest scientist, you cannot change your data. So your y sub i's are fixed values, so are x sub i's. Your parameters here are a0 and a1. So again, S sub r is a function of a0 and a1. The x and y are just parameters in this case, or data that you can't change. And if we want to minimize, this is actually a two-dimensional optimization problem. What we are actually trying to do is calculate the gradient of SR and set it equal to 0. In other words, we are trying to calculate a vector, which is the partial of SR with respect to A0, and the partial of SR with respect to A1. And we want this to equal the 0 vector. So let's do the derivative. So this is del SR, the partial with respect to A0 is going to look like minus 2 times the sum of y sub I minus A0 minus A1 x sub I. And the derivative, so remember I'm taking the derivative here, right? The derivative of a sum is the sum of the derivative of the individual terms. The 2 goes out front, right? That's where this 2 comes from. And the negative I'm also moving outside. And then this is what's in here, right? When I said the 2 goes out front, I think I should have done this, and then the negative comes from the chain rule. So now if you calculate DSR dA1, then what you're going to get is minus 2 times the sum I equals 1 to n of x sub I, y sub I minus a0 minus a1 x sub I. Okay, so it's a similar procedure except the derivative is with respect to a1. And instead of just getting a negative out of the chain rule, you also get an x sub I. And so this is equal to 0. In other words, 0 vector. In other words, both components are equal to 0. Let me write that out a little more explicitly. So sum of all the y sub i's, that should be n, where n is the number of data points, so that's the first equation. I think I'm writing a little too big here. Let me make a little more room. And the other equation from the second row is that the sum I x sub I y sub I minus a0 sum on I of x sub I minus a1 sum on I of x sub I squared equals 0. Okay, so again, I just distributed out this x sub I, so that's x sub I y sub I, this is a naught x sub I, and then a1 x sub I squared. And then I pulled the constants out of the summations. And so I have two equations in two unknowns. And let me do a few other manipulations here, and also highlight a few things. So this is a constant that we know. This is just the sum of y values. So remember, y corresponds to data. So you have a series of data points that we drew over here. So the sum of y sub I is just the sum of the vertical positions of each of those data points. So that's a constant that we can readily calculate. A0 may not be something we know, but adding it to itself n times is going to give us n A0. That's, I believe, the definition of multiplication. And so, once again, this is the sum of x values. So again, that's the horizontal position of each of these data points. Again, something we can calculate. So these are constants. Notice that this is also a constant. You take each data point, you multiply its x and y value, and then you add up all those for all the data points. Now, notice this is also a constant. And so is this. So this is just the sum of all the x values. Here you take each data point's x value and square it and add all those numbers together. So what you have here is a linear equation. So this A0 is just proportional to n, its coefficient is n. A1 has the coefficient, which is just this constant that we can calculate. Likewise, you have constant coefficients of A0 and A1 on the other equation. So to put this into matrix form, we have n sum of x sub I, and this is the sum these are what we're trying to calculate, and this is the sum of y sub I and the product of x and y. So this is a matrix. This is a matrix of quantities we can calculate, and this is a matrix or a column of quantities we can calculate, right? So we just need to solve this to calculate the best fit line. So in another video, I'm going to use MATLAB to actually calculate the best fit, but I want to actually point out something that isn't actually so easy to see here. There's another way to formulate this this matrix problem, and you'll see why I'm pointing this out in a minute. So an alternate formulation so if I were to define a matrix Z, and I'm going to say that Z is equal to 1, 1, 1, 1, dot, dot, dot. So there's going to be n rows. In other words, number of rows equal to the number of data points. And here I have x1, x2, x3 through xn. So I have a column of all my my x values for each data point. Then it can be shown that my best fit parameters, so A, which are going to be A0 and A1, are going to equal Z transpose Z inverse times Z transpose Y. Oh, and I should have defined Y. So the vector Y is just Y, Z, well, I guess it starts at 1. Y1 through Yn. So this may seem rather complicated or bizarre, but this is also relatively easy to calculate. So you can calculate Z, right, just from your X data. You can calculate Y from your Y data. And I'll show in MATLAB that just plugging in this formula, Z transpose Z inverse times Z transpose Y, is going to actually spit out the same best fit parameters that we got from this equation. So when you go to the coding, I think you'll find that this is actually easier to code. Not that it's that hard to code the other way. I think the main advantage to this is what I'm about to explain. So something that that you may not be aware of, and this is known as general least squares. I think it's called general linear least squares. So it has been shown, I'm not going to go through the detailed math, but it's been shown that if I'm trying to do regression according to a formula that looks like this, actually, wait, I think I use B's, B0, Z0 plus B, my hand still wants A's, not B's, Z1 plus B2, Z2, BM, ZM, and your Z sub i's are functions of X, are defined functions of X. Then it can be shown that you actually have a linear regression problem. Let me make this a little more clear. So in the case of a polynomial regression, so for example, what I said was that we were going to investigate B0 plus B1x plus B2x squared. I was pointing out that this is actually linear regression and that Z0 equals 1, Z1 equals x, and Z2 equals x squared. So because you can express this problem in terms of linear combinations of parameters and defined functions of x, that this is actually a linear regression problem. So in this case, your matrix Z takes the form Z0, 1, Z, 1, 1, Z, 2, 1, dot, 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 ZM1. And what this actually means is that this is actually Z sub ij is going to be Z sub I evaluated at x equals x sub j. I'll use an example a bit later. And so this is going to be Z11, Z, I think I got this. Oh, no, yeah, this is right. So, well, actually, no, this is wrong. Z01, oh, sorry, Z02, and this is Z12 dot 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 ZM2, and this will go through n data points. So this is Z0n through ZMN. And so in the case of the quadratic, these will all be, so in the case of the quadratic, let me just copy this. In this particular case, Z is going to equal 1, 1, 1, dot, 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 x1, x2, x3, x sub n. And this is going to be x1 squared, x2 squared, xn squared. And this formula that we talked about for linear regression still applies. So with this more general definition of Z, whoops. So this has to be amended. So this would be B0 dot 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 B sub n, because the number of functions that we use for Z right here, actually this is not n, this is m. Hold on, how do we count these? Yeah, okay, that's right. So these are the parameters that correspond to the coefficients of each of our functions. And this can be applied to more complicated linear regression problems. Now, do notice that when I first presented this equation, this matrix would have been the first two columns of this matrix, right? In this sense, if I were to ignore B2 or force it to equal 0, then this becomes just standard straight line linear regression. And so this formula is, you could think of as an extension, recognizing that linear regression just means that your function that you're trying to fit is linear in all of your parameters. It is not necessary for y to be linear in x, right? So if you have something of that form, then you can fit. So one of the examples I'm going to do is I'm going to look at quadratic data. So the last thing I want to talk about is the theoretical treatment for nonlinear regression. So it is not always true that your function is linear in your parameters. So in the case of nonlinear regression, we can use a very similar approach, but it's going to have a very important difference. So I want to say, so if you take my class, then you probably have heard this often. If you have a linear problem, so say a linear system of equations, then this ends up mapping to a matrix problem that you can solve by inverting a matrix or performing Gaussian elimination. If you have a nonlinear system, what you usually do is you linearize, and in the case of a system of nonlinear equations, or a nonlinear system of equations, you linearize by calculating the Jacobian. So that's something I'll talk about elsewhere. But when you linearize, your solution, so linearizing creates a matrix problem, but the issue there is that that matrix problem is only an approximation of your actual system of equations. So then what you do is you introduce iterations. So you guess the answer, and then you refine the guess. You check error. And if the error is not good enough, right, so in other words, usually the simplest way to check error is to see how much your guess changes between the initial guess and the refinement. And if your guess is changing by too large an amount, you need to continue to iterate. So the way you do nonlinear regression is to use the Gauss-Newton procedure. And so what you do in the Gauss-Newton procedure is you use the following update formula, which looks pretty similar to what you are used to, or what we actually just went through. There is an important difference. So delta A, which is the change in all your parameters, is going to be Z transpose, I'm going to call this Z sub J. I'll explain what that means soon. Z sub J transpose Z sub J inverse times Z transpose D. Okay, so it looks similar. So this is the change between guesses, or the update. So in nonlinear regression, unlike linear regression, you have to start by guessing, right? You have to guess your answer. And so this is going to be a vector of how much you need to change relative to your guess. So we need to redefine Z, and this, by the way, should be Z sub J. So Z is something that is going to change each iteration. So what is Z? So remember that you're trying to fit y equals some function f of x and then a0, a1, dot, dot, dot. So some number of parameters. And so what z is going to be Z sub j is going to equal df1 dA0 df1 dA1 d. And what I mean by this is that this is going to be df A1 evaluated x equals x1, right? So the first data point. And so now this is going to be df2 da0 dot 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 and df2 da1. So it's going to be, again, the same function, f, right, this f. But when I say f2, what I mean is I plug in x equals x2. And we're going to go through an example of that. And so that's the z sub j. But remember that every time you do an iteration, your parameter guesses are going to change, right? So you have to recalculate z sub j every time. And now there's this other matrix D, which is new. So D is just now going to be y1, the data point, minus f of x1, a0, a1, dot, 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 y2 minus f of x2, a0, a1. So in other words, D is going to be a vector of all the error terms, right? So the difference between the measured y sub I and the predicted y sub I based on your current guess for parameters. So let me just summarize the Gauss-Newton procedure, which I'm going to go through in another video. You start by guessing your vector A, which is A0, A1, and then you calculate delta A such that your new A vector, I'll call it j plus 1 or something, where j is your iteration, equals A sub j plus delta A. And then you repeat. And so in general, the standard thing that we do in my class is we use an approximate relative error, which is just going to be A sub I j plus 1 minus A sub I j over A sub I j plus 1. If you want it to be a percentage, you multiply by 100. It's important to take the absolute value because we are not concerned about whether an error or an update is positive or negative. But what this is looking at the change in each parameter between iterations. And usually you want to repeat until the estimated error for all of your parameters is below a certain number. Say 1% or 0.1% or something that implies that if your algorithm is not changing your guess by much, then your answer should be accurate.